Okay, hi all. Good evening. We are from Group 11 and the part of MMIR Assignment 2. And myself, Prabhakar, and I have my teammates Krishna and Shravani, Anubhav Agarwal, and Venkata Hanuma, Surya Hanuma. Yeah. So we are going to explain about our assignment to problem statements and what we have done and what we have implemented. This is a group assignment, so that's why we want to give a small brief about this project. Yeah, Anubhav, please go to the problem.
Yeah.
Yeah. So there are two problem statement here. One is a text to video retrieval on MSR VTT, that Microsoft Research Video to Text Data Scale, and second problem is a cross model audio retrieval on audio caps. Okay, so both the problems we did, all five of us, and yes. So the about problem one statement, we have done two things. One is an encoder, where we are using dual encoders. It is like a encoder, shared space, nearest neighbor ranking, and went for retrieval metrics. But there's a difference in the encoder, that data set, and the specific question of each investigation. Yeah. So for problem one, the text to video retrieval on MSR VTT, the data set and setups are like we pulled from the Hugging Face data set using the standard 1K split 1,000 test videos with one caption each. That is one is to one retrieval setup, and the 9,000 training split, from which 2,000 unique videos are sampled to keep this training traceable. Okay. So actually, these are .mp4 clips and downloaded and decoded there. Yeah. So yeah, Krishna, you want to go through that implementation plan?
Yes, Prabhu. So here we compare two different approaches for converting the embeddings of 8 video frames into a single video representation for text to video retrieval. The first approach is our baseline, which uses mean pooling. Here we simply take the embeddings of all 8 frames, calculate the weight average, apply L2 normalization, and directly compare the resulting video embedding with the clip text embeddings. Since no additional model is trained, this represents a pure zero shot clip approach and does not capture any temporal relationships between the frames. The second approach is our temporal model, which uses a learned attention pooling mechanism. Instead of treating every frame equally, we add a small temporal attention pooling head on top of same frozen clip frame embedding. This attention module learns to assign different importance to different frames, allowing the model to focus on the most informative parts of the video. The attention head contains approximately 1.3 million parameters and is the only component that is trained. For training, we use the 2000 video training subset. The model is trained for 15 epochs using the Adam optimizer with a learning rate of 1 times 10 to the power of minus 4, a batch size of 64, and a temperature of 0.07. We optimize the model using a symmetric info-NCE constitutive loss, where the learned video embeddings are aligned with the frozen clip text embeddings. Throughout the experiment, the clip image and text encoders remain completely frozen and are never fine-tuned. Finally, to ensure a fair comparison, we evaluate both approaches using the same 1000 video test set. Their performance is measured using the standard retrieval metrics like recall at rate 1, recall at rate 5, at rate 10, median rank, and mean reciprocal rank. Yes, Shram, you can go forward.
Shravani, you're mute. You're on mute.
I'm sorry. So when we come to the specifics of the result, the recall at 1 for the baseline is around 0.2%, and for temporal it's 14.6, and the recall at 5 is 0.6 for baseline, 36.2% for temporal. Uh, Recall at 10 is 1.5% for baseline and 50.6% for temporal. So here, we can see that temporal has outperformed the baseline one a lot in this task. So the median rank is 485 for baseline and 10 for temporal. Mean rank is 488 for the mean pool baseline and 45.5 for temporal. MRR is 0.0089 for the mean pool 0 short baseline 1 and 0.2575 for the temporal attention pool, the trained one. So and qualitatively, for a query, a person is playing guitar on a stage. The baseline returns cartoon clips, while the temporal model returns bands, instruments, and stage performances, which is it's clear the unrelated cartoon clips are um, way unrelated compared to the temporal one, which are more interpretable results. Improvement. It is more improvement than the baseline one. Here we can say that the attention pooling model, it dramatically outperforms the mean pooling one on every metric here. So we can conclude that the uniform, we should be moving from beyond the uniform frame averaging, which is more useful in this task. Yeah, thank you.
Yeah,
Oh,
thanks, Sura. Anubhav, go, please.
yeah. So, moving on to our second problem statement. This was a cross-modal audio retrieval using natural language queries. So, for this, the dataset we used is audio caps. It's a publicly curated audio dataset with human level text. It has around close to 50,000 audio clips, each of 10 seconds. We loaded it at 48 kilohertz using Librosa, and we used a model named Lion Clap. That's a multimodal model for representing audio and text in same dimension space. We used a 512 dimension space for representing our audio and text together. And this is a ML spectrogram MFCC chart for one of our sample recordings. The x-axis you have the time in seconds. The y-axis contains the frequency. It's a time distribution chart for our audio sample, and this is the model which I was talking about, a contrastive model. Uh, Using this, we actually represented our audio samples into a latent space, and using the text that is the natural language, we intend to query them and use it for retrieval. Uh, the approach will be better explained by Hanuma. Over to you, Hanuma.
Yeah, thanks, guys. So now, in this case, right, what we did was our approach was aligned with the clap, where we kind of had audio and text encoders that kind of map both into a shared space. We retrieve the clips using the cosine similarity, which kind of measures how closely the representations align. In the live demo that we kind of built, we built a gallery of around about 2000 clips, and then we did a search for heavy rain with thunder in the background. All of the top 5 results contain rain and thunder. That's a good sanity check, kind of reassuring, because even the research models should occasionally agree with common sense, right? Now, for the quantitative evaluation, what we kind of did was for each of the 4,815 test captions served as query with its paired audio as the single correct result, right? Then we kind of measured recall at 1, 5, and 10. We also did MRR, MIP, BCG, and median rank. Recall at 10 kind of reached to 36.97 percentile compared with about 0.2% by chance, and the median rank was 18. Overall, I think the findings give a qualified list for the research question that we had, and CLAP kind of captures meaningful cross-model structure, although retrieval performance can still be improved. Thanks, everyone. Thanks for the opportunity.
Thanks, all. Yeah.
Thank you. Thank you, everyone.